Hello everyone, and welcome to today's presentation on searching in arrays. In this session, we'll explore two fundamental search algorithms, linear search and binary search, and understand how they work within array data structures. Let's get started. Today's agenda is as follows. We'll begin with an introduction to searching algorithms. Then, we'll dive into linear search, discussing its process, implementation, and complexity. Next, we'll cover binary search, examining its method, implementation, and time complexity. We'll include visual demonstrations to help clarify these concepts. Finally, we'll compare the two approaches and look at their use cases. This roadmap will guide our discussion through each important aspect of searching in arrays. Searching in arrays involves locating a specific element or determining if that element is absent. Efficient searching is crucial in data processing and algorithm optimization. In this session, we focus on two main techniques. Linear search, a straightforward, sequential method. Binary search, an efficient, divide-and-conquer approach applicable to sorted arrays. Understanding these techniques is essential for designing effective and efficient algorithms. Let's start with linear search. The concept is simple. Traverse each element in the array sequentially until you find the target element. Key points include: it's intuitive and easy to implement. It works on both sorted and unsorted arrays. It's particularly useful for small datasets or when the array isn't sorted. This method checks each element one by one until the target is found or the end of the array is reached. Here's the pseudocode for linear search. Start from the first element. Compare the target with each element sequentially. If a match is found, return the current index. If no match is found by the end of the array, conclude that the target is not present. The steps are: initialize an index counter, iterate over all elements, check each element for equality with the target, and return the result accordingly. On this slide, we have a visual demonstration of linear search. Watch the animation as it sequentially highlights each element in the array, showing the step-by-step process of comparing elements to the target. This visual aid helps to clearly illustrate how the algorithm works. Let's discuss the time complexity of linear search. Worst case, O(n), when the target is not present or is located at the end. Average case, also O(n), since on average you might need to traverse half of the array. Best case, O(1), if the target is the first element. Additionally, the space complexity is O(1) because it requires only a constant amount of extra space. Now, let's shift to binary search. This algorithm is designed for sorted arrays and works by repeatedly dividing the search interval in half. The precondition for binary search is that the array must be sorted. It is especially useful for large datasets, where its efficiency can significantly reduce search times. Here's how binary search works in pseudocode. Set two pointers, one at the beginning, low, and one at the end, high, of the array. Calculate the middle index, mid equals low plus, high to low, /2. Compare the target with the middle element. If they are equal, return the mid index. If the target is less than the middle element, adjust the high pointer. If the target is greater, adjust the low pointer. Repeat the process until the target is found or the search interval is empty. This method efficiently narrows down the search range with each step. On this slide, you'll see a visual demonstration of binary search in action. The animation shows how the search space is halved with each iteration. Notice how the algorithm quickly zeroes in on the target by eliminating half of the remaining elements each time, a clear illustration of its efficiency. Let's look at the complexity of binary search. Time complexity, both the worst case and average case time complexities are O log n because the search space is halved with each step. Space complexity. For an iterative implementation, the space complexity is O(1). For a recursive implementation, it is O log n due to the extra space used by the call stack. This efficient performance is what makes binary search so powerful for large, sorted datasets. We are done enough of talk. Let's code the pseudocode which we have discussed for linear search and binary search. So to do that I am going to Visual Studio Code. So guys, I am into the Visual Studio Code. We start by defining a function called linear search. This function takes an array, its size, and the target value we wish to find. It goes through the array one element at a time. For each element, it checks whether the element matches the target. If it finds a match, it returns the index of that element. If not, it eventually returns -1 indicating that the target isn't present. Next, we define a function called binary search. This function is intended for sorted arrays. It initializes 2 pointers, low and high, to mark the boundaries of the search interval. Inside a loop, the function calculates the middle index, mid, and compares the element at that index with the target. If they match, the function returns the mid index. If the target is greater than the mid element, the search continues in the right half by updating low. Otherwise, it continues in the left half by updating high. This process repeats until the target is found or the interval is exhausted. In the main function, we first demonstrate linear search using an unsorted array. We define an array with these values. The target value is set to 23. We call linear search with these parameters and store the returned index. Depending on the result, the program prints a message stating whether the target was found and at which index, or that it was not found. Next, we demonstrate binary search using a sorted array. We define a sorted array with these values. The target value for binary search is set to 32. We then call binary search with the sorted array and the target. The function returns the index where the target is located, or -1 if it isn't found. The program prints the corresponding message with the outcome of the binary search. N. The program clearly shows how both search algorithms work. Linear search examines each element sequentially, making it suitable for unsorted arrays but less efficient on larger datasets. Binary search, on the other hand, leverages the sorted order of the array to drastically reduce the number of comparisons needed, showcasing a more efficient divide-and-conquer approach. Now let's run it. And when we ran it, it throws error as I did a silly mistake. I have given space-separated file name that is not allowed here. It is throwing file not found. Let me rename it by removing the space. Now we have done the changes. Let's run it and you will notice that it run and given the output. Linear search found 23 element at index 2 and binary search found element at index 3. Now we are done with the code. Let's go back to presentation. Here, we compare the two search algorithms which we have implemented in this session. Linear search. Pros, simple to implement, works on unsorted arrays. Cons, slower on large datasets, with O, N, time complexity. Binary search. Pros, much faster with O, log N, time complexity when applied to sorted arrays. Cons, requires the array to be pre-sorted and has a slightly more complex implementation. The choice between these algorithms depends on factors like dataset size and whether the array is sorted. This comparison helps you decide which algorithm to use based on your needs. Now, let's discuss when to use each search algorithm. Linear search, best suited for small or unsorted datasets where the overhead of sorting isn't justified. Binary search, ideal for large, sorted datasets where the efficiency gains significantly impact performance. Best practices, always assess the characteristics of your data before choosing a search method. If repeated searches are expected, consider whether pre-sorting the data for binary search is worthwhile. This slide highlights various use cases and provides practical tips for selecting the right search algorithm. In conclusion, both linear and binary search are fundamental algorithms for finding elements in arrays. Linear search is simple and versatile, but binary search offers superior performance on sorted arrays. The choice of algorithm should be based on dataset properties and performance requirements. I now invite any questions or further discussion on these topics. You can post your questions in comment box. On this note, I am stopping over here. See you in the next session.